and notices to present first before I hand over to David. So, good evening, welcome everybody. My name is Toby Johnson. I'm the chair of the Railway Division South Eastern Centre. Thank you very much for joining us tonight. It's good to see we've got a good turnout again. I would like just to remind everybody that we are going to be recording tonight's talk. So just be aware of that fact, and we will try and upload the recording to the YouTube channel that the IMechE hosts. So it will be available at a later date to rewatch. So welcome everybody. As I said, there's a few quick announcements that I wanted to make before go over to our main event, which is our presentation tonight on the Barking Riverside Extension of the London Overground network. I'm sure you're all looking forward to hearing about that. So I'll make my notices as quick as possible. I just wanted to start off by making sure that everyone is aware of the current situation around Birdcage Walk. So I'm sure many of you are aware that current IMechE headquarters is at 1 Birdcage Walk. There are some plans that have been in development to develop this building. All I want to do today is just signpost you to go and have a read and stay informed about this important development for the institution. It's quite a change, and I think what needs to happen is that we all make sure that we read the information that is available online on that hyperlink. There are webinars to attend as well if you want to learn more, and also an opportunity. There's also an opportunity for you to have your say. There are plans to have a member vote in December on the IMechE's plans. So hopefully you've all already seen some communications around this, but if you haven't, hopefully this little signposting is helpful, and you can go away and have a read and get yourself informed about this situation with institutions' main assets, really, apart from its members, which is its building. So hopefully you've all had a chance, if you haven't already, just to write down or click on that hyperlink and go and have a read of that another time at your leisure. So secondly, just to make you aware and put in your diaries of our next event, which is entitled Rails Recovery from COVID-19. We will be hosting the event at Birdcage Walk, all being well, fingers crossed. And that will be on the 15th of November. So we've managed to secure Neil Ovenden, who is Head of Engineering at Rail Delivery Group. He's going to talk to us about how the rail industry recovers from the effects of pandemic on passenger numbers on the railway. So please head to our near you websites for online registration. So that's 15th of November. Get that one in your diaries, and hopefully we will see you at one Birdcage Walk to do some long overdue networking and hopefully some socializing as well. So I'm excited by that one. But on to tonight's event, which I think is going to be a very good presentation. So I'm very pleased to introduce David Mansfield, who's Programme Engineering Manager, who's going to talk to us tonight about Barking Riverside Extension. David, over to you.
Okay, well, let's hope this works. Hang on, let's try this share button thing again.
Oh, I should have said we'll have a question and answer session at the end. Feel free to pop your questions in the chat function, and if you can just keep your microphones on mute until we get to the end. Apologies, David. Back to you. Thank you.
It's okay, no problem. Good evening, everybody. It's nice to see quite a few names that I recognise from my past. My name's David Mansfield. I'm the Programme Engineering Manager for London Overground's Projects Division. Barking Riverside, I'm trying to give you an overview of the entire project from why it exists to things we considered in design, what's happened in delivery, where we are today. It should be entering service sometime autumn 2022. A few reasons behind that, mainly to do with access on the railway, but it's all going really well at the moment. It's been an incredibly short project. When you see what Barking Riverside is, when you consider we only started design in 2015 and achieved Transport and Works Act approval within 18 months of starting design, and then we're into delivery with lots of early works and other bits and pieces. It's been really quite fast moving. I led the design team from the initial concept through to the detailed design. So that's my involvement in the project. Although in delivery, I'm more supportive, more in terms of track systems, rather than being what Network Rail termed the designated project engineer, because I've got too many other projects on the books and I can't cope with everything on my plate at the same time. So Barking Riverside, why does it exist? Well, first off, London Borough, Barking and Dagenham has got a large number of growth hubs within it, and they've got massive opportunity to deliver a wide range of new jobs and housing across the borough. So one part of the vision is Barking Riverside. It's the largest brownfield development in the UK, 10,800 homes with, as Barking would put it, superb River Thames frontage. At one stage it was mooted to be Barcelona-on-Thames. Beam Park Ford stamping plant. So with the withdrawal of all heavy industry from the Barking and Dagenham area, there's a lot of other brownfield sites that are available. Part of that is the Beam Park development, which is providing 3,200 new homes, another new station actually on the Tilbury Loops, and over 1,000 new jobs. And potentially in the future, the scheme referred to as Castle Green, underground in the A13, and unlocking the potential for it's a minimum of 5,000 new homes around a new station on the route that we're actually building at the moment. And we'll cover that in the presentation. Since writing this slide, other things have happened. So Billingsgate Market is now moving just around the corner from Barking Riverside. There's a new film studio being built in Dagenham East, which is not that far away from the development as well. There's a huge amount of growth going on in Barking, and Barking Riverside is just part of the transport enablers for that. So Barking Riverside in the future. What you can see on the slide there is the developers' plans and aspirations for what the development will look like, and the red line is the extension off of the national network that feeds the rail line into the Barking Riverside development. Transport connectivity in that part of the world is fairly bad. On completion of Barking Riverside, there will also be, and you can see it there on the River Thames outlined in red, the old pier that was used actually to dispose of spoil from Crossrail and bits of High Speed 1 will be brought into use as a riverboat service to Canary Wharf and central London. So it won't be just purely relying on rail and bus services for future travel. Just capping on what we said already. So Barking Riverside, it's a key development area. The Riverside development is the largest housing development in the London area. The project outturn cost is £327 million. Transport for London are not paying for all of £327 million. Barking Riverside Limited is a condition of their planning to basically fund the rail link. We began construction in autumn 2018 and train services are going to commence in 2022. The delivery of the extension will unlock a wide range of benefits for people in the local area and beyond. The 10,800 new homes, many of which are actually affordable, along with a new school, which is actually now open and in operation, and healthcare facilities as well. The construction of a new district centre with commercial and leisure facilities, and it's now rumoured that there's going to be a mini O2 type events amphitheatre thing there. Train service interval that we're going to be running will be a forecast train service at 15-minute intervals, so that's 4 trains an hour, and Arriva Rail London Limited will operate the services on behalf of TfL. The stakeholders that we had to work with in the development of the scheme initially was Network Rail, the Strategic Freight Network, Barking Riverside Limited, London Borough, Barking, Dagenham, DB Cargo, Legal and General, who own a huge amount of land that we had to build our railway over. High Speed One, which was interesting. Lots of line-side neighbours, really from a land and boundary fencing point of view. It is not just the extension to the network that we're building that's the problem, it's the fact that we had to reinstate the old abandoned down goods line from Barking all the way down to where our railway diverges. That runs through a heavily populated corridor. It was a 3-track railway, it's now a 4-track railway, and we had, I'm trying to remember how many now. About 90 4-track hourly portal structures to construct at the bottom of people's back gardens, and all of those were driven piles. So neighbours was a key concern during the development of the property, the proposals. New schools, when there's a new school in the area and you're bringing a railway to the area, you have to consult with those and also make sure that the pupils are aware that what you're doing is introducing something that is inherently somewhere you don't want kids to be playing. And the train operating companies and freight operating companies as well. Tox and Fox was quite a lengthy period in negotiation and development of the scheme, ensuring that timetables worked. And the freight operating companies has got interested ever since Brexit as well, with the massive increase in containerised freight from Europe into the high-speed one exchange sidings. Very early on in the project, we assessed the options for what we would be doing in terms of the build strategy for the project, and we decided on a build-only contract with Rail for London Overground providing a Grip 5 design to the successful bidder. Our designers were required to produce a design that was deemed to be fit for purpose instead of the normal reasonable skill and care. The reason we went for a fit for purpose clause, which did have to be underwritten by insurances for the designer, was that fit for purpose means that you are building something that can be defined and hung on the purpose that you state for the assets when they're constructed. Reasonable skill and care is actually quite loose in terms of the way it can be interpreted. Level of design and integration at completion of design than reasonable skill and care gives you. Having said that, the GRIP 6 to 8, so the construction, design and commissioning contractor, we still have some design work to do, and they have been doing that. They have responsibility for secondary steel work, detailed rebar on reinforced concrete, precast concrete systems, proprietary systems. They're wholly accountable for temporary works design. When we're talking about signalling, they're responsible for SSI data. They're responsible for all the staging design for overhead line systems and for signalling designs. They're also responsible for collaboration with Network Rail's Telecoms Group, NR10E, and Network Rail's Comms Field Services on aspects of the fixed telecom network and the fixed telecom network next generation than GSMR works. Interestingly, London Overground, it's me and my team, we're delivering this under a scheme of delegated authority. Delegated authority is interesting. Normally, if you're an outside party to the national network, i.e. Network Rail, you're managed under an asset protection agreement. By using the scheme of delegated authority, we managed to satisfy Network Rail that we satisfied the requirements to be a association. which massively reduces the amount of oversight the Network Rail undertake as part of your works. So in effect, Network Rail were required to approve the approval in principle design, and myself and my engineers did the approvals for the detailed design, and then we managed the design process, implementation, and hand back to Network Rail as a self-assuring organisation from that point onwards. Took a couple of years to get the agreement in place, but it was there when we started doing the job. So first off, there's existing infrastructure east of Barking Station. We reinstated the abandoned down goods line as a new up Riverside, and we'll get into that in a bit. On that section, there's 3 kilometres of new ballasted track. There was 13 renewed 4-track OLE portals. There was 8 new 5-track or more OLE portals. The longest OLE portal we actually ended up building at Ripple Lane West was 45 metres side to side as a self-supporting structure. There was 62 new simple overhead line structures. We had to renew 3 overhead line neutral sections. In total, and this goes back to the bottom of People's Gardens, there was 102 OLE piled foundations. A new 40-mile-an-hour crossover from the upwards to the up Riverside. This will make sense in a bit. And a new 50-mile-an-hour connection from the down Tilbury to the new down Riverside. And also we remodelled Ripple Lane West sidings to give us the footprint to squeeze the new Riverside lines through in that area. That was 10 renewed point ends. Within Ripple Lane West sidings, there was a kilometre formation remediation, and everything was basically re-signalled with associated TPS and AWS infrastructure where it was needed. When we actually come off of the network and onto what we've built, the extension to the network starts with a 300-metre long approach span, which is founded on a ground slab. We'll get into the geotechnics of it in a bit, but that required 240 number 450mm diameter piles driven to a minimum depth of 12 metres. There was a 50-metre long retained fill ramp leading to an E-type steel underbridge over the down through goods line. Then we ended up with 11 number 40-metre long, shouldn't be 11, sorry, got that wrong figure. 7 number 40-metre long steel and concrete composite bridge spans, an E-type steel deck over a highway, and then onto the main concrete viaduct that runs down to the new Barking Riverside Station. That's 43 25 spans, and the way that they are articulated, in effect, we've got 25-metre spans with 50-metre decks, so they're fixed in the middle, 3 ends at either end. To build that block required 560 1.25 metre diameter piles. These were CFA auger piles, and they were driven bored to a depth of 30 to 40 metres. We also had a little challenge around the up Tilbury line, 1.4 metre diameter piles to form a new box over the up Tilbury. We'll cover that in the presentation. They went down to 40 metres depth as well. And then the worst piles that we had to do was 9 piles that were 1.5 metres in diameter to 40 metres deep between the high-speed one running tunnels. And we'll cover that in the presentation. There's 1.5 kilometres of twin track slab track, and on the viaduct itself there is 52 and another 3 kilometres of Series 2 overhead line equipment. Those are just the high-level stats on what the railway consisted of. So what that will give us is new infrastructure that supports the 4 trains an hour service. It also supports future service requirements for C2C. So when I referred to the TOCs and FOCs earlier, we had to do a huge amount of timetable modelling to prove that the future service requirements and aspirations of C2C matched with the you have to put in for the London Overground service. Also, we had to factor in the effects of Bean Park Station, which is being built just down the road. In fact, it's about 800 yards away from where we split off from the railway. We also had to clear all of the sidings that currently exist in Ripple Lane for GB2 gauge for high-speed 1 freight. Only one road was cleared for high-speed 1 GB2 freight, and unfortunately, as part of our scheme, that became a head shunt and got somewhat shortened, let's put it that way. So we had to gauge clear everything else in the area for continental gauge freight. And we also had to cater for 2 trains an hour electrically hauled freight in the peaks as well. The last point on this slide isn't actually accurate any longer. There was issues with the 25 kV feeder station at Barking because there was perceived to be problems with the incoming cables needing renewal by UKPM, which meant that, in effect, Barking feeder station was derated, but during the life of the project, the feeders were reassessed and pressure tested, and the feeder station is now working at its full capacity again. These slides have this office, and we didn't really have time for this one to go through and update everything, so that's a little bit out of date there. But it actually made us do a lot of traction power modeling, and it's given us a more robust feeding scenario for Barking Riverside anyway. So that was a benefit, even though at the time it was somewhat of a pain to try and work out what the hell to do to get power to the extension. So what were the changes that we've made on the network? On the top there on the diagram in black is what the railway looked like before we started playing with it. And on the bottom in red are all the bits that we have added, changed, modified, or generally just messed around with a bit. It's hard to see there, but the big group of sidings that you can see somewhat towards the middle is what we call Ripple Lane sidings. And you'll see, if you stare closely, that all of the junction work, it has moved to the left towards London. The junction work moved by about 100 metres towards London, and that was part of the remit we gave to provide passive provision for the future lengthening of those sidings to accommodate 775 metre long freight trains. Provision of 775 metre freights on the network is something that is a good thing that everybody wants. And in fact, we were requested by Network Rail to develop a full approval in principle design for those sidings to be built as a 775 metre scheme. We did that, delivered it to Network Rail, and when we finished Barking Riverside, that scheme then kicks off, and eventually, hopefully in about 18 months' time, 2 years' time, Ripple Lane West will be capable of accommodating 5 metre long freights, probably with one on the departure line, and if it can be squeezed, one on the up goods, the other side of the station. So it will become what's deemed to be a nodal yard, and that will give Network Rail and the freight companies the ability to stack freights in the Ripple Lane area and then flight them across London in the off-peak periods when you can potentially reduce your passenger service and get more freight running across London. To the right, you can see that there's a piece of magenta there, which is the new extension to the network, and that goes from the DB Cargo Euro hub lands over the Up Tilbury, over high-speed 1 exchange sidings, and then down to the new station on the banks of the Thames. Our design philosophy, we decided to keep it simple, stupid, because I'm getting old and I don't really have too much time to be thinking about things that are novel and challenging and developing them. And also, we wanted to modularize things as much as possible. The more you can modularize, the more you can standardize on the installation methodology, the more that you can build the same way off-site and bring to site and plug together and make it work, the quicker that you can actually build the project and the cheaper that it gets. You don't want to get into novel technical solutions on site if you can possibly avoid it. So one of the first things that we did, we thought, right, okay, we'll standardise on 610mm LME tubular piles for all overhead line structures. And we later expanded that to include all signal structures, including the the massive signal gantry we had to build across the entire railway down there. That went on the Lemmy pile foundations in the end because the CFA pile foundations didn't prove to be viable, because High Speed 1 wouldn't let us through their compounds to actually get the CFA rig to site to build them. We adopted Network Rail standard design ENU decks for bridge structures. We adopted the Y8 precast concrete beam solution for concrete viaducts. We resized them and used them in as many configurations as possible for anything that we had to build on the viaduct or the station. Basically, we used the design that had already been proven at Reading on the Reading Viaduct. We also developed modular viaduct parapet units with standard blisters for overhead line structures, so things can step out from the side of the viaduct. And we designed them in such a way that they could be modularized to take location cases and track equipment housing base locations, track lubricators, access stairs could plug into them, you name it. You could do it all with the one modular unit that we designed. Some of the problems that we had, geotechnical, this was a real head scratch. The ground conditions in the Barking area, bearing in mind it's on the banks of the Thames, they're extremely variable. It's alluvial deposits. There is peat to 5 meters depth in places, very high water table up to 1 meter below ground level. Lots of people actually thought the water table down there was going to be tidal. It isn't. As we get to the Thames, piles have to go to a depth of 29 meters minimum, so we can get to good end bearing pressures. And we had to oversize all of the piles as well due to ineffective upper lengths and the shear forces we're going to get within that. And also from the geological records, one of those you can see there, which is from the British Geological Survey, shows that there's potential for faults to be present within the geology and the strata in the area. That concerned us. So rather than just relying on simple boreholes, we also undertook some pretty detailed geophysical investigation of the ground, just to map out and see exactly what it was we were getting down there in terms of densities of soil and soil characteristics and behaviours. Boreholes are all well and good, but they're expensive and you can't do them everywhere. Geophys is good and you can cover a large area. And what you can see there on the left is some of the geophysical results that we got from doing the ground penetration radar and the resistivity surveys over the brownfield site. Mapped against what was there from the geological mapping records, and there's fairly good correlation. There were a couple of areas where we found things that we didn't expect to find. I couldn't actually find a slide that showed one, but there was some faulting that we were really worried about, but we actually managed to redesign some of the piles that we could miss a pretty massive fault that was in the formation down the formation ground. When we got onto the actual national network itself, the formation and trackbed that we decided to adopt was completely compliant with Network Rail standard 4239 for formation and trackbed. It is incredibly soft and incredibly variable though. So in critical areas like under the new 50-mile-an-hour diverging turnout, we used micropiling to stabilise the ground underneath. We also have used wherever we had to use them. One thing we have introduced since then as a value engineering exercise was to, on the sidings and on the new Riverside, to remove the dead load from the existing formation that you would introduce as a result of using heavy concrete sleepers like G44s. We went with steel sleepers. Steel sleepers are lighter than concretes, but they do work really well on soft ground conditions. And I proved that when we were doing lots of steel sleeper renewals on the Fens back in the mid-2000s. It's all to do with precess waves and radial wave velocities, in effect, trackbed critical velocity issues. It's worked well, and the steel sleepers enabled us to increase our delivery rates on some of the plain line sections. Gauging, as we referred to earlier, gauging on the route was done as per normal, using clear route 2 for passenger running lines through an agreed vehicle line. Ripple Lane siding 1 was the only siding up there that was currently clear to GB2 gauge. But as siding 1 disappeared as part of our scheme to all intents and purposes, any alterations to the sidings, and that included the upwards and the departure line towards Barking, were also to be cleared to GB2 gauge because they were currently foul. In actual fact, it was only 3 signals that were currently foul to GB2 gauge, as we found out. At the time, ClearRoute, which is one of the standard pieces of gauging software, couldn't handle GB2 gauge, so we had to go down the road of using defined gauging as required by BSCN 5273. That was a bit of a challenge, but we managed to get that undertaken. And one interesting part of the project was that we required a blockade to undertake some works on the Up Tilbury line, and we needed to block the Up Tilbury line in that area for 6 weeks. There is a diversionary route for freight. That means freight wouldn't have to travel over that section of track, because the train operating company, C2C, was quite happy for that blockade to take place. However, when we started looking into the diversionary route, we noticed there was a few areas where there were speed restrictions in place for freight. We identified what was causing those speeds, and then we corrected those so that we could increase the speed for freight on those sections and not affect the C2C timetable on a normal working timetable day of the week. What we actually found was that platform 1 at Upminster was foul to every freight gauge that it was currently clear to. So we undertook works there with Network Rail to restore the gauge capability on the diversionary route. So what we ended up with on the sidings down there, so a typical cross section, is going from left to right is the Down Tilbury, and then next to the Down Tilbury is the new Up Riverside. And you can see the trackbed treatments there. Then continental freight gauge on them, and then on the right hand side we've got the Up Riverside. That's the tightest point at the London end of the sidings, and that's also one of the very long self-supporting portals that we had to build to provide electrification to the new Up Riverside and also to the third road in, which is Down Goods. Interestingly, all of the overhead line portals that we built also had to cater for the future extension of those sidings, the 775 metres. So some of them are a lot longer than they appear to need to be, but they won't be when those sidings get straightened out in the future and become even longer. Don't really think we want to look at this. Right, okay. I'll skip through that slide. It runs for a long time. Some of the challenges that we had. Probably the biggest challenge that we had on the project was the high-speed running tunnels. See there in red is the model of the viaduct, the steel composite structures that are travelling over the railway lands. I hope you can make out the high-speed run tunnels that are there roughly about 15 metres below ground level and diving down to go towards Stratford. The only way that we could make the design work in terms of articulation of deck ends and getting everything to work properly was to provide a particularly long span there. That's a 40 metre long span, which would need supporting in its middle, but we couldn't support it at right angles to the track because to do so would have meant piling through both of the high-speed one running tunnels, which probably wouldn't have gone down that well with high-speed one. So what we ended up doing was piling between the 2 tunnels. That took a lot of agreement to high-speed one. To give you an idea of how close we actually got to the tunnels, each one of the high-speed one running tunnels has got a 3 metre annulus around it, which is a no-go area. And thou shalt not go within that 3 metres. And there's a 2.5 metre gap. Sorry, not 2.5. There's another 3.5 metre gap between the 2 annuli. And we had our piles at 1.5 meters diameter that had to go straight down in the middle of that gap between the two annuli. CFA board piles to 40 meters deep. It's pushing the limits of what you can do with CFA piling. That was successfully carried out. We had monitoring installed in the tunnel. We used a meshed array provided by Sensieve. We surveyed the tunnel ourselves, modelled the tunnel ourselves, imported that into the model. So we had a full model of track, we had a full model of the tunnel. There's a cross passage that's very, very close to one of the piles. There's only about 700 millimeters between the passage. Doesn't look like it there in the diagram, but it is. And we managed to do that successfully without a cover speed on high speed ones. So they were running, well, not exactly 24/7, but they were running without a cover speed while we were boring between their tunnels. And we never hit one of the trigger limits. We had an awful lot of stuff set in place there. That's what to do if we suddenly started getting unpredicted movements in the tunnel, like uplift or displacement. We learned fairly early on that the high-speed one trigger limit per meter was probably not a good thing to adopt, because every time a train went through on high-speed one tunnels, we got triggers. But eventually we got things settled down, and that section went really well. The problem with those piles is they, in and of themselves, couldn't fully support the bridge deck above them. So each side of them, there's another set of piles that had to be built in a more traditional pile group, pile cap arrangement, and then tied together with a ground slab just below ground level so that everything acted together. The one problem with the single row of piles is they would be subject to flexure, so that ground slab ties them together completely. And just on the right of the image there, you'll see, and it's hard to make out, something that looks like a little box. We'll get into that in a minute, but there is a bridge deck joint there above the up tilbury, and we couldn't do anything other than do what we did there. We're not 5 degrees on the slab track. In fact, for ballasted track, that's probably a pretty good limit to run to anyway, and be Eurocode compliant. That would have meant that the pier that supported that deck went straight through the middle of the up tilbury. Realigning the up tilbury was not possible, so we just built a very short tunnel, and we'll cover that in a minute. A few more bits on the high-speed one bit there. I've already covered all of this. The piling was carried out under liquid support with bentonite. I think I've covered all of that off. Oh, the only other thing that we did have to do was work out how to transform the CTRL grid to OSG B36 grid and then into LSG 2007, which was the engineering grid for the project. That taxed the minds of an awful lot of people. In the end, University College London spent 4 months working out how to transform between the 3 grids to actually get something right. I was talking about the box over the up tilbury, and I've also spoken about the works that we did at Upminster to gauge clear. We had here. In a 6-week blockade, we had to build foundations. The reason we took a 6-week blockade was to do it. Doing it a known weekend session. Only get one pile session every weekend. That was just 6 weeks. Those And what you're seeing now is the follow-on works as predicted by the computer modelling. 4D modelling. And now you can see the bearings going up the plinths for the support for the new viaduct structure that go over the top. Which is all very nice in terms of 4D modelling, but this is what it actually looked like in reality. It's full work. This is after the blockade. We've returned the railway to operational service now. It's the process of returning it to operational service. All of this work is being done in weekend possessions. We're doing other work. So what you're seeing here really is pressed into a couple of minutes. It's probably fair to say that this box is one of the most difficult things to build that we've had to do on the project. Oops, don't know what happened there. Sorry about that. I seem to cut that short. I won't go back. We don't want to go through that again. So many other challenges that we had. Choates Road and the ultra high voltage transmission lines. We see the vertical profile. Just impression of what the service would look like in the future. Yes, that's a 2-car class 172. We're using 4-car class 710s. But one of the problems we had is we've got a public highway, and immediately adjacent to the public highway, we've got a series of the 250 kVN and 125 kVN transmission lines that cross the railway. That's the vertical profile that we had to design to deal with the problem. From the left to the right, we're sort of rising up to get over the railway lands and over high-speed line running tunnels, over the high-speed line exchange sidings, and over to the other side of the railway. We then have to get over Choates Road, but then we have to dive down massively to get underneath the overhead transmission lines. It was really threading the eye of a needle on this one. It's incredibly difficult to find an alignment that meets the requirements that gives you highways clearance, and then also electrical clearances from the transmission lines. So a person stood in the bucket of an RRV maintaining the overhead line equipment. When you actually put all the figures together for what you require for electrical clearances and safe clearances as per BS 50122 part 1 and that, we ended up with a 100mm tolerance window within which we could actually put our rail level. Very challenging. At the same time, we had to make sure that all of the track gradients were compliant, all the equivalent gradients were compliant because of the curvature of the railway at that point. So going from left to right, we're sort of reasonably straight as we rise up the viaduct. We go down as low as 225 meters radius. We then carry on a 225 meter radius before straightening out to go underneath the transmission lines, where we've got that compliant electrical clearance. What it does do at that point is actually drive the viaduct so low that the soffit of the beams that support the viaduct are only about 2.6 meters above ground level. So the viaduct itself is 1.5 kilometres. We said already, concrete, steel viaduct and composite bridge spans. There's 1.5 kilometres of twin track slab track. On the viaduct itself, there's 52 twin track OLE portals. We've now got quite a few single track cantilevers in there to improve signal sighting. And there's Barking Riverside Station at the end. Spoke about the viaduct construction earlier on. You can see there it's pretty standard stuff: piles, pile cap, pier, Y8 beams, deck slab, deck, intermediate slab, track, and then parapets at the side. Nothing novel. Oops, don't know what's happened there. Oh, the actual viaduct itself. This is some footage that we took with the drone last year. That's the station that we're just exiting. It's in October. Showing you this because what we do here is actually explain some ways. So the station 392 decks. That's see all there. And this is what we start. You can see the development going on actively in the background there. That's for the homes that will be leased for sale once the extension is in operation. Yeah, lots of ground stabilisation because the ground conditions are so poor. Intermediate deck slabs, they're cast in that checkerboard pattern because they all have to act independently of the main bridge deck. That way you get over some of the problems with track bridge interaction. Not the access part of the structure.
David, I think we're having
That gives you an idea of the sort of volumes of materials that we had to play with just to actually build viaducts. In terms of what we did with the ground, how much concrete we've used, which no environmentally is. Oops. Can I go back? So that's just a quick overview of the viaduct itself. The ramp and the viaduct track form. We had some real challenges with this. So it was a 1 in 40 gradient cresting to a 225 metre radius curve. Welded rail for noise limitation. And obviously you saw how close we are there to properties. There's going to be a lot more development in the area. We have to use CWR, and the only way we can do that is going to be the slab track. It's a very steep gradient to get over the high-speed one exchange sidings over Choates Road and under the transmission lines before rising back up again to give permeability beneath the viaduct. One thing the developer wanted was they did not want a railway running at grade. So that would basically cut it off from the land on the other side. And to be perfectly honest, if we built a railway at grade anyway, it would have been a viaduct at grade because the ground conditions are so poor. So we would not really have saved anything by going at grade through there. It's fair to say we're pushing the limits of what you can do with slab track. I'll get into that in some more detail in a minute. But basically, we decided to carry out some pretty detailed modelling as to what we could do. So the 225 metre radius curve, in actual fact, it turned out at the end we did the whole viaduct. We modelled that using Vampire and Dynamis to determine the best track parameters for performance, especially T-gamma in terms of what was going to be happening for the propensity to develop rolling contact fatigue. We modelled the line speed, which is to be used, which is 40 mile an hour, but we modelled it with a 10 mile an hour overspeed and underspeed. We modelled the infrastructure with and without check rails. We modelled the infrastructure with and without gauge widening because of the curvature. We modelled it in tear and crush. And then we modelled it using a theoretically overly torsionally stiff primary suspension to produce high angles of attack in the wheel set to see what actually occurred to the rail and especially the damage indexes and T-gamma. And that work was carried out by the University of Huddersfield. What we did find was need to do too much. With the various variations in track gauge, the variations in applied count and vehicle speed, the unchecked case results in only marginal changes in Y over Q and wheel lift. Y over Q, the propensity for derailment, so Poisson's ratio, if you like, the figures were really good, incredibly low. We didn't expect to get that, but we did. So much so that the case for a check rail to limit the propensity for derailment was marginal, eliminated the check rail from the design. The main driver behind us doing that was that check rails, when you do get flange contact with check rails, make a huge amount of noise. If there had been a definite positive delta in having a check rail there in terms of limiting the risk of a derailment, we would have kept a check rail, but there was basically nothing in it. So getting rid of the check rail will limit any noise radiated into the environment. T-gamma forces. Again, we found what we thought we were going to find anyway, which is that T-gamma actually bounces around all over the place. If you have a check rail or if you don't have a check rail, I mean, the check rail will always reduce the T-gamma on the high rail because it's the back of flange that's taking the force, hence the noise. But none of the T-gamma values that we were getting again were high enough for us to believe that we had particularly high risk of RCF being so tight. So we came up with a series of recommendations as a result of modelling. For crush laden, and is every train going to run crush laden on a route? Probably not. But the peak Y/Q value was found to be 0.37 relative to the limit value of 1. Now, that resulted in a peak wheel lift of 0.8 millimetres relative to a limit value of 6 millimetres. And as would be expected, those peak values were predicted to be for high rail flanging wheel in the unchecked case. That's a very nowhere near a point at which we get concerned. Normally with Y/Q, we start to get concerned around 0.75, 0.8. So we're well in the comfort zone there. Additional simulations for the class 3, 4, 5 in the tear condition and modified tear conditions have resulted in only a marginal increase in the maximum recorded Y/Q to 0.42. With a corresponding wheel lift of 0.88 millimetres, and both values remaining significantly below the limit levels. The reason we said a class 3, 4, 5 there was that it's an Aventura unit. They both use the Bombardier EcoFlex Series 4 bogies. The behaviour of a class 3, 4, 5 from a class 7, 10 or even a class 70, to be honest, and we had that modelling that was available. And under the conditions, as I said, simulated, a check rail was not required to mitigate against flange climb derailment risks, as indicators remain consistently low in an unchecked state. However, fitment of a check rail would offer increased derailment protection containment in response to unforeseen events. However, we couldn't make it work from the economics point of view and also from the potential environmental effects of high levels of noise. We were quite happy to go down the road of not having a check rail, and all of this was discussed in detail with the technical authority, Brian Whitney. With regards to gauge widening, there was no significant net benefit found. All cases studied were at a high cant efficiency, greater than 80 millimetres. There wasn't any significant additional benefit demonstrated in reducing the applied cant, i.e. increasing efficiency from the proposed design value of 100 millimetres down to 50 mil. And hence, from a passenger comfort perspective, it was recommended that the applied cant stayed at 100. It was noted there was, in a number of places, the applied cant levels and speed studied resulted in excessive cant deficiencies of 122.6 millimetres. But those were theoretical overspeed events. So if the line's actually driven as it should be driven, you don't hit those excessive cant deficiencies. But we wanted to know where we get to if there was overspeeding occurring. Now, another thing that I'm interested in, the Viaduct track form. The Viaduct track form is not particularly new or novel. We're using STA, manufactured by Por in Austria. It's a mod has been used in the UK, in other places. It's never been used in the sort of environment that we've used it in embarking, i.e. such tight radii and on such steep gradients. But it has been installed. It's in Glasgow Queen Street tunnels. It's on the Gospel Oak to Barking line, through Cratchhill Tunnel, and in the Walthamstow Queens Road area. There's quite a bit of it through there. So we've learned some lessons from that, but we've had to develop the system further to put it on the viaducts that we've built. That's what the viaduct track form looks like on line VDEI8 in Germany. There are what we call USP, BSP plates, and we'll cover those in some more detail in a minute. The reason I say we'll cover those in more detail in a minute is we found some problems. One of the problems that you have with slab track is the limits that you have for deck end rotation. The deck end rotation is specified within the Eurocode, so that thou shalt not exceed 2 milliradians of deck end rotation. By and large, the viaduct passed, but there was areas where it didn't quite work. Now, deck end rotations can be managed. It's worth noting at the time when we started the design on this, all that we had was the Eurocode 1, BS 1991, parts 2, 5, etc. In parallel, there was a work stream being undertaken by the SEN committee on slab track, which resulted in the publication of paper SEN TR 17231, which made recommendations as to how you could overcome the deficiencies within the Eurocodes, and with that means that slab track on viaduct structures can sometimes get itself into a little bit of trouble. The little bit of trouble that we're talking about is a thing called axial rail stress, or more specifically, reserve axial rail stress. So why is it an issue? Interaction between the track structure and the bridge structure, i.e. the consequences of the behaviour of one of those structures on the other, occurs because there's a physical connection between them, whether the rails are directly fixed or there is a ballast bed in between the track and the bridge. That interaction results in forces being applied to the track, rails, fastenings and ballast, and the bridge substructure, the foundations, piers, abutments and bearings. And those forces are in addition to those which would be expected if the track and the bridge were analysed separately. What tends to happen is that the structure, and they will take account of the factors that sit in the Eurocode, such as load model 71, an alpha factor of 0 or 1.5. They'll get a set of results that they're reasonably happy with, but they won't go deep enough into the track system itself to see what the effects are on the actual physical components of the track. And that's something that this NCR paper addresses. So as I've already sort of wimbled on about, Eurocode 1 defines the requirements for design of structures and traffic loads. The code itself, it addresses the basic requirements for structural performance for specific load cases. It doesn't address the impacts of that on the track system. And so Eurocode 1, wonderful thing, but it doesn't really help you when you start considering the requirements of EN 13481 Part 5, performance requirements for slab systems, or for EN, damn, I've left that 2 in there again, 13643, ballasted track systems. That one's interesting because ballasted track systems, Euro, you have high-speed applications, although it does refer you back to EN 15528 for line categories. When we say high-speed applications, all of the Eurocode calculations consider high speed, i.e. 200 kilometers an hour or higher running, and they consider a minimum radius of 1,500 meters. Barking Riverside, we're running at 40 miles an hour, which certainly ain't a 225 meter radius. And the load models that are contained within the Eurocodes don't really apply. They don't downscale and give you accurate results. So when you're in a low speed tight curvature environment, that leads to structural designs frequently leaving the track system with complex issues to resolve, and that's the case that we had in Barking. So once we downscaled everything, the track system failed using load models 71 loads for rails and rail stresses. So just to quickly go into it, deck end rotations, axial rail stress, Eurocode load is 200 kilometers an hour, min radius 1500 meters. It's SEN 60 rail. We're using SEN 56 rail. It's got load model 71 in it. It's got load model SW0 and the alpha factor of 0 to 1.5. And as I said, the Barking design was started in 2016 before the SEM paper was published that made recommendations that addresses a lot of these issues. But basically, a huge swathe of the Eurocode needs to be rewritten so it becomes useful across the piece. So we had this problem with the deck end rotations being too great. It's in excess of 2 milliradians. So on ballasted track, where concrete sleevers would be used, the principal effect would be rapid deterioration of the ballast, resulting in twist development at deck ends and a reduced asset life. Now, bear in mind, because of the transmission lines, we couldn't use ballasted track at Barking Riverside because the construction depth for the ballasted track would be so deep that we couldn't get clearance under the high voltage transmission. On a slab track system, that's fine and dandy because you've got a slab track system, but the mitigating factor then becomes the fatigue and stress limit of the rail fastening and the stress capacity of the rail itself. Now, we could get over the first part of that by adopting a Deutschesbahn design for the USP BSP plate. That's a very resilient plate and clip. We used that on the first 3 rail seats, abutting the 3 deck end USP plates. That then gave us the problem with the stress capacity of the rail to solve. USP plates, this is the plate that we ended up developing, say copying from Deutschesbahn, because we just used the same plate and modified it for 756 by Schwehag, who manufactured them for Deutschesbahn. And ended up looking like that for Barking Riverside. One thing to note there is we've got yellow Voshlow type clips, sorry, SKL clips. They're low toe load clips, which is one way we can help to reduce the axial rail stress, because we can have a lower SFT in the rail by using low toe load clips, not zero toe load, low toe load clips. And then we've got the highly plates at each one of the 3 deck ends. So we know that we're going to have a problem with axial rail stress. High local rail stresses can be generated by 2 main mechanisms: opening and closing of the joint by axial displacement of the bridge deck ends, or by movement of the joint due to the rotation of the bridge deck ends. And there's other mechanisms that come into play here: thermal effects of the track, the substructure, and traction and braking forces. Traction and braking, the speeds we're talking about, aren't really that significant. We have to consider a huge amount of things to actually determine what it is that we're doing. We wanted to understand what an acceptable level of reserve axial rail stress is. We know what the limiting axial rail stress is, i.e. at which point the rail is going to break. So what we were interested in determining was how much stress were we putting into the rail, and so how much reserve axial rail stress was available to us that is believed to be reasonable within Europe. And did we actually breach any of those values? So there's a huge amount of things that you have to consider and think about. Your static wheel force, it's all there in the table. I don't want to go into it in detail because I'll be here going on for hours. And then your various formulas. One interesting thing is if you actually follow the TSI clauses for lateral track resistance, which is what most Novos and Devos will insist that you actually carry out, you can carry out the calculation quite simply for a system such as a Barking, and that will tell you that everything's okay. So that we had a maximum permissible lateral force of 13.97 kilonewtons, which is great because that's within the rules. But again, these rules are defined by the Eurocode, one could argue, isn't valid when you're at low speed, tight curvature arrangements because nothing scales downwards. So even though we were compliant with the clauses in the Eurocode for lateral track resistance, we weren't compliant with the requirement for what we're doing with axial rail stresses, which isn't expressed particularly well. So what we ended up doing was modelling the system, carrying out an awful lot of sensitivity analysis, looking at the way that stress is distributed throughout the rail, from the centre line of the rail to the edge of the rail foot. Our worst case is always going to be what is the stress at the edge of the rail foot, because that's where if you have any form of nick or defect or potential stress raiser, that's where your stresses are going to be highest, and that's where the risk of propagation of a break is going to be worst. So what we actually worked out was that using a load factor of 1.3, because we didn't want to use 1.5, because 1.5 would equate to a 25.5 ton axle load, and class 720 trains are only a 15.2 ton axle load. We could reduce the load factor. We could reduce some of the stress factors within the rail by using those so-called clips. And work out that the reserve stress available within the rail at the joints where we're using the BSP plates was just above the proposed 112 megapascals limit. The proposed limit is the limit that is in the CENTR paper. So we have a proposal to monitor that in service. That'll be the first time it's ever been done. We are not aware that anybody else has ever monitored the axial rail stress at the 3 worst case locations on the structure when it goes into service, and get a year's worth of data to see what it's doing. Switches and crossings, the track form for that, we carried on with slab. On the left there is the genesis of the base plate that we're using at Barking. I saw that at Intertrans in 2015, and having sat down on the manufacturer stand and taken it to pieces and put it back together again, thought, this could work. So we spent some time developing that plate. That's now fully approved on Network Rail and installed on the Viaduct. Again, that's on line 8 in Germany, where it was undergoing trial evaluation for high-speed running on Deutschesbahn. So we've ended up with a rail fastening system, which is the Schwehag SW system. It's pretty cute in the way that it operates. Go into that in a bit more detail. The clips that you can see there, they are in the team colours for this year's McLaren F1 team, because I'm a McLaren supporter and I had the opportunity to put whatever colour I wanted on the clips. So I got a bit cheeky there for a minute. It's a modular system for the S&C base plates. As many of the components within the system as possible can be used in different configurations, which we had quite long and hard to ensure that all of the parts could be manufactured and basically Legoed together before they actually become part of the slab when it's cast in. It's a pretty typical sort of system that you're going to see for slabs. So you've got the support layer, you've got a support layer plate, you've got a resilient plate, you've then got the rail base plate, you've then got the rail pads, you've then got your rail and your rail clips, and you've got your standard Vossloh dowels with SKL clips. It's pretty much a piggyback system. It differs quite radically from what's been done on S&C on slab before. We took a different approach to resilience. If you're looking at other S&C systems like Sonneville and the likes, other bits and pieces, they're designed for a deflection rather than a static stiffness. So what we have done, they're designed for static stiffness, not for deflection. So we've flipped it on its head. We've designed the system to actually deflect by 1.5 millimeters throughout, varying the stiffness of the support layers. There's less force and wear on the components within the system. It's the pad that does the work. It's not the rail and the fastenings that does the work. The point operating equipment is first of type in the UK, Voestalpine Unistar electro-hydraulic. It's cost effective, drives like a clamp block, it's wired like a HW, uses standard HW SSI data. It is fully tradable up to 40 kilometers an hour with no damage to either rail or machine. There's no stretcher bars required. It's seal4 rated. The failure rate is expected to be in the region of 50 years. There's actually one mean time to failure is 68 years. It solves a multitude of problems with the point operating equipment on slab, and it builds on work already done by Anna Cornish at London Underground. I've got my final safety case meeting on it in a couple of weeks' time with Network Rail, and today I'm in Edinburgh doing training on Unistars with Network Rail staff for the first deployment, which is and then our 60 Mark II 1 in 28 switch diamond that goes into use at 100 mile an hour at Christmas. That's what it quickly, and where I'm overrunning my time. 2 drive units at Barking, and sized, and it's sited such that someone can always be in a place of safety when manually operating it. Won't bother with that. Station visualization. Apparently Barking is a place where you feel like you're coming home. The station cross section, you can see that we've reused the Y8 beams wherever we can do in different configurations to actually form the station. Nothing particularly spectacular or wonderful about it, but again, just an example of how we modularized throughout the project. Follow-on projects after Barking Riverside, there's Castle Green Station, Ripple Lane sidings, which I've mentioned already. Barking Riverside Station itself has got active provision for 5-car services and for 6-car. It's on a viaduct up in the air, so we took a conscious decision to future-proof the station. I won't go into Castle Green Station into too much detail, but at the bottom there is the Barking Riverside development. The bit at the top there is the proposed additional housing, and where the little red squiggle is where Castle Green Station would go. We've already designed it, as you can see there. And we've already built the infrastructure with a big nothing in the ground area between the 2 tracks, and also constructed the overhead line at a height that's compliant with the platforms going there in the future, and sited the signals for the station in the future and modelled that, so that when that station is built, it's done with the minimum fuss and bother. Ripple Lane Noble Yard we've already discussed briefly. What Ripple Lane Noble Yard does is straighten out the bits that we've finished and extends the sidings further towards country, as you can see there. And just winding up, this is what it looks like. This is what it looked like on Sunday, actually. So this is running down towards Barking Riverside. This is going up over the existing railway lands, Tilbury lines and High Speed 1. Running down towards the school. Looking back. The pictures don't do it justice. Some of the gradients we've got and the way the rail actually rolls its way around the curves and the transitions is actually quite mind-blowing. And that's the switch and crossing work going in at the moment. Just some thanks there to the guys in my team that have been part of this, but particularly from outside of the network, people like Guy Bates from the Strategic Trade Network, Brian Whitney at Milton Keynes, the CEM at the joint venture as well, and the guys who actually undertook a lot of the design, like Paul Malford and Nick Arms. My thanks to them, and finish boring you. Right.
Brilliant. Thank you, David, for such a in-depth presentation. That was fantastic. Really interesting. I have to apologise to our attendees. I don't think we had the chat available during the presentation, but no problems at all. We will go for questions now. So if anyone would like to ask a question, if you could use your raise your hand, and then we can get you to unmute your microphone and ask David your question. Right, so first hand went up there was John Ryan.
Hi, thanks, Obi. Thanks, David, for the very in-depth overview of the entire Barking Riverside project. My question is just regarding the snake grids interface, and you mentioned some works from UCL. As we're going forward with some of the big projects, we've got HS2, Crossrail and Tideway and other projects. What was the lessons learned for future projects with respect to interfacing with bespoke rail kind of snake grid coordinates and kind of mapping systems to enable us to go off and better coordinate future works?
Snake grids at Barking don't really sort of come into it, John, because I mean Barking's basically on the east-west alignment, and snake grids only really come into play when you're going north-south, because we're not that affected by the curvature of the Earth. But I get where you're coming from.
Was there any lessons learned from the UCL one for future projects, though, for interfacing with, you mentioned it was 3 different grids tying together, and you had a lot of head scratching around that. Was there any kind of lessons learned that came out of that from the UCL team that you got involved?
The one lesson learned was we all thought CTRL would actually have a copy of their survey grid and their control, and they'd actually have geospatial information on their tunnels. But as it turned out, they didn't. So we had to recreate it, and from that we had to also recreate the original CTRL control so that they could establish things back into their archive records that they had patchy copies of. I suppose the only thing we really learned was that, yeah, it's nice having LSG 2007, which is basically the derivative of Crossrail 09 as a grid. The big thing we did learn was, though, don't rely on OSGB 36, whatever you do. It's just not accurate enough for our needs. We did work out that density of grid is a really good thing to have. You've been there before, John. You're speaking here from NLRIP experience, aren't you?
Yeah, we didn't learn either in Tideway, so it's also Tideway tying into other developments around London.
The main thing is make sure that any project that you're on, make sure that when you establish a grid, you control that grid, you record that grid, and you maintain records of that grid and the grid parameters, especially the primary and secondary control points. If you've got those and you keep them as hard records, you can do anything in the future. If you lose them, as High Speed One might have done, it becomes difficult because you have to then try and re-establish something. You don't know what the baseline is you're shooting for, but we did get there in the end. Yes.
Thanks for that.
Okay, does anyone else want to ask a question? Don't have any hands up. I'm assuming, then, David, that you covered everything in sufficient detail that no one's got any further questions. I mean, I was wondering. Obviously, this is well. My question really is around maybe more around the business case of the project, and that it's delivering a service to the people who will be living at Barking Riverside development. But there seems to be quite a bit of secondary benefit in terms of the other train operating companies and indeed the freight services. Was it originally conceived that way, or were they seen as opportunity works to enhance the project?
You broke up a bit there, so I didn't get your entire question.
So my question really was the business case for the project conceived purely as the passenger service, or whether the benefits that we saw that you explained for the freight services?
Yeah, it's purely a passenger service. Yeah, so for us, it was purely the intent of Barking Riverside is to provide transportation to the Barking Riverside development and that ward of the London Borough of Barking and Dagenham. The ward itself is one of the most deprived in terms of transport connectivity in the UK. At one point, it was the 3rd most isolated community within a town or city in the UK. It's served by 3 bus services. The buses run every 6 minutes. They are full day and night. It currently can take you 45 minutes to get from Barking Station to where Barking Riverside will be. and the train service will do it in 7 minutes. Yeah, it is being built purely to green station. You could argue there's a potential business case there because we all know that the demand radius around the station is about 900 meters. You could actually expand it to cover areas that aren't within the footprint of the new station we're building at Riverside. But at the moment, of course, funding constraints post-COVID, and that is proving a bit difficult to find funding for schemes such as that. But we've designed everything so that station can be built quickly and easily when it's needed. So it did trigger a lot of debate about the future of the freight network and operations in the area, which is why we got given Ripple Lane to do, and we did. So
Great, thank you for that. Kevin, you've got your hand up. Do you want to ask a question?
Yeah, thank you for that. Very interesting talk, David. Thank you. Just wondered whether you could tell us more about kind of the system integration sort of challenges, signaling and control being obviously one of those, in terms of how that all knits together within a wider rail
it's
context.
not been that difficult. It's not been that difficult, to be honest. Most of the existing railway looks pretty much the same as it was before. There's one interlocking boundary that we have to move purely for a signal workload perspective. We don't have to provide any new interlockings because we can piggyback off a spare capacity in Purfleet interlocking 6. That's not been difficult at all. The hard part has been potentially some of the comm side, changing from FTN over to FTNX for the SSI data links. No, surprisingly for once, the signaling side has not been the massively difficult part of the project. The thing that really caught us out that no one could predict was COVID, because we lost our Easter commissioning in 2020. And straight away that put our program, because that was going to be our big on-network commissioning. So now we're scrabbling to find access to take our up into the box to do the big final commissioning that we need to do. And it's proving difficult because during COVID, we went into Brexit, and up until that point, we'd been quite happily working away weekend in, weekend out, getting possessions on the running lines. And then all of a sudden, all this freight appeared from Europe that had never appeared before. Now you can't get access to get on the railway. So it's been a bit of a delay impact. It's a good thing for UK PLC that we're getting this freight coming in by rail.
Thanks, David. Thank you.
Okay. Any more questions for David? I can't see any hands. Well, that's probably a good point then to wrap up. And just say to David a great big thank you from us at the IMechE Railway Division South Eastern Centre and everyone that's attended. You've given us a really in-depth talk on the whole Barking Riverside Extension project. There's obviously a wide range of stakeholders and beneficiaries of this scheme. Talked us through some of the most considerable challenges, like piling in between two high-speed rail lines. You explained how we also got some secondary benefits of to our freight services and how that's benefiting the UK. Been some considerable issues with the ground and the geotechnical fault lines that were apparent in that area, and how this project has really taken those and tackled those issues and delivered what seems to be a really magnificent extension for the overground network to, as you say, one of the most isolated communities in an urban area. So I think that's really fantastic, very commendable. And I'd just like to say once more, thank you very much for your time tonight, and yeah, the presentation was fantastic.
Okay, thanks very much. It was a pleasure to give it. Sorry I overran, I always do.
No, not a problem at all. And thank you very much, everyone who joined the meeting tonight. It was great to have you along and make the event a real success. Hopefully you can join us on the 15th of November for our talk on recovery from COVID. And I will hopefully see you then. Thank you very much and good evening.
Good evening all.
Thanks, guys.